Today I wanted to talk about a rational design process for operational amplifiers. I actually don't think I was able to do that and ended up kind of doing a design by sweep. It doesn't mean the equations aren't valid, it's just the constants push around so much um, that you kind of have to simulate everything. So let's just have a review. The gain of a common source amplifier with an NMOS is minus G times its output resistance, which uh, can be approximated by GM times the early voltage divided by the current that at bias. And then if you just manipulate it, there's your GM over ID times your early voltage. So that's what your gain is. Right, then if you had a PMOS load instead of an ideal current source, which has infinite output resistance, right, you just have the output resistance of the N in parallel with the output resistance of the P. Which just lowers it. So if we make the same assumption about that the output resistance is the early voltage divided by the bias current, well, the bias current is all the same, right? But we have an early voltage for the N and an early voltage for the P, and we just put that into our parallel combination. But again, we can pull out the ID and then just have this combination of the early voltages, and if they're pretty close to each other, we just see that the gain is reduced by half. Now if the load of the PMOS has an early voltage a lot bigger than that of the NMOS, right, where we had a cascade current mirror type thing, right, then we get right back to where our ideal was, or very close to it. Now, for the differential amplifier, and I'll show you the structure later, right, we should still have GM over ID VA divided by 2. That's assuming some kind of PMOS load where this isn't true. And then if we want to, we have a differential pair times a common source amplifier. This would be an NMOS, this would be a PMOS circuit. We just get GM over ID squared times the early voltage squared. And for about 1/4. All right. Now, it turns out that this VA isn't a constant, but it depends on the bias current quite a bit. So let's just go back and review a few things. So I want to do the GM over ID technique, so I diode connect this MOSFET. Right, I'm going to sweep this voltage from 0.1 to 5 and measure the current. This is all in the 122 manual. Okay, so there's that. We take the derivative of that, and there's our GM. Right, now our GM over ID is that. This should be a current, which is ID M1, and it's a lot better to look at it in a logarithmic scale. Now you can zoom in make it a little prettier. Right, and so this should be our GM over ID. Now, I extracted the gain, or the early voltage. I was getting about 41. So yeah, I should be getting the maximum gain, about 968. But the thing is this 41, it's changing all along this curve. And what I found is that at about 2.5, actually gave me kind of closer to the maximum gain. Now, how did I measure that? Well, let's just run this simulation. And here I have CS out. I'm sweeping V in, and I have IL at 2.5 microamps, LN at 10, WN at 30. The lengths of the NMOS and PMOS the same, and the PMOS width is twice the NMOS width. So this should give me like that ideal gain. And because I've measured it automatically, I should just be able to go to the SPICE netlist or the error log, scroll down, and I get about 736, which was pretty close to what I got over here. So just let me put it at 2.5. I was getting 653 here. And when I view the SPICE error log, it's off by 100. The thing is that the VA is super sensitive, and I just can't extract it exactly at the right spot. All right, but that's pretty good. Then I set up a current mirror for a PMOS load and do the same thing, and yep, the gain goes down, which was as expected. All right, did it go down by exactly the same amount, by 2? Almost, but VAN and VAP are not exactly the same, right? So it just gets reduced, but still, not quite less than 2. All right, so that's a little more realistic. Now let's go to the differential pair with an ideal current source here, and I'm going to have to rather than extract it. Alright, so that's, I'm sweeping, and V out goes high and then goes low. And if I just take the derivative of that, that'll give me the DC gain. And so I'm getting about almost 500. So this was giving me about let's just look at it again. This was 700. Then with just changing the load, I got minus 446. Then Right off of that differential pair, I get about 500, and so still that's pretty good, right? Now, the next thing I want to do is find what's the gain when I have a PMOS current source. So that's one gain, then I'll multiply by the other gain. And remember, this would be a complete op amp. So I have the gain of the differential pair, the gain of a common source NMOS. I should have GM over ID squared times VA squared so not sure if this will work. Okay, and by 4. So I should be getting according to that model, I should be getting 104, a gain of 104,000. Now, not really. And we'll see if I look at the at the gain of this with the ideal current source loads here, I get a gain of 31,000. All right, so it's off. At some point, you just have to kind of keep going and just say, well, it has to do with the differential pair. And oh, actually, I needed to extract the GM over ID of the PMOS, which I didn't do. So in fact, I that's probably where the error is that I assumed that the GM over ID was exactly the same, but it's not. Well, there's an NMOS and a PMOS, and so and the VAs are different. All right, let's hope that just paused. All right, there might have been a technical difficulty right there. Anyway, this is the common source, and basically it's got a different VA, and so it's estimate. So anyway, we got 31,000. All right. Then I thought, what about if now we put, instead of current sources, we actually put the NMOS transistors, right? So this sets up the current mirror. That bias voltage goes here and here. And that gave us almost a gain of 30,000. Which you know, 89 or 90 dB, right? Which is pretty darn good. Now, that's great sweeping it, but we really don't know what the offset voltage is. And And so I'm just going to use these two as an example. Okay. And we can see that the gain is going towards infinity. It's slightly different. B, possibly the more accurate. But just trying to read off where the max happens just by this is a little bit hard. So what I thought was we would have a circuit that would measure the offset voltage. Now this is from the LT1006, where you have two resistors of the same value, then you have 100. This 100 ohm is from here to here, and then these two values are the same, but they're swept. And I had a feeling that the output voltage is divided by the gain, and the gain is a non-inverting op amp, and so that resistance is changing, right? And yeah, this output voltage, the offset voltage is minus 474, goes down to about almost minus 0.5 milli, and then comes up. And I have a feeling that's just there's errors due to the gain, right? But you can see that it's less than a milli, which is pretty good, right? Because we want to use it as an integrator, right? Now, the spice file is here. I just hid it so that you don't have to look at it. And I thought it was a lot easier just to put the Howland current pump in this configuration. X2 is here on the inverting, X1 is on the non-inverting, right? And set up these current sources. The values are all the same, right? But first, let's look at the AC analysis. All right, and that's very integrator-like. The gain is, the phase is mostly minus 90, right? Then it drops down. And here's the you all right. So something that I added to this simulation is that there's the area of the NMOS drain and sources, and the perimeter of the drains and sources, and essentially when we get into layout you'll see what these things are, but you have to calculate them, right? Now the thing is that assumes these fixed LNs and WNs, but if I want to have let's say study the mismatch, right, rather than try to adjust WN and LN, I can just make this 1.1 times bigger, right? And you can see that I'm still getting integrator-like activity, but when we look at the transient, we'll see that's not quite the case. Trying to really get it. Anyway, so that That is very, very integrator-like, right? And if you just plot 1 over S, you'll get the same value. So we have a working integrator. Now, it's always good to kind of check things more than once. Sorry, something weird. No, I didn't know I was up to 32 transistors. So let's do a time domain. Right. And all I'm doing is so the time constant is 1, right? And I'm on for 1, and so I go up almost 1. Then I'm -1. When I integrate -1, I get a slope of -1. So I keep kind of going back and forth. All right. So this is, kind of everything's ideal, no mismatch. But if I make this like a little bit bigger, all right, just 1.0. So this transistor is just whiter than expected, right? You can see that it starts drifting up, right? If I make it smaller, it'll start drifting down. Now the thing is this isn't actually such a problem for us because every time we go above 1, we're going to reset the integrator back to some other number. So this is just kind of, I mean, yes, there's feedback, but in a way, that positive offset voltage is just being integrated over time, right? But every time there's a spike, right, um, it just gets reset. So it seems that this structure is pretty tolerant. Um, Now, yeah, if I make one of them twice as big as the other, uh, the drift happens very quickly, right? And then it's just bouncing on the positive power supply, right? It gets here and then it integrates down. But even still, even with this kind of horrid shape, as soon as I crossed, it would reset. So it's just integrating some always this constant DC, which we could probably handle on the input where we take that into account. So a little more confident about what we're doing. Still, now we can, if the offset voltage is too large initially, it can be problematic. And so we might have to, for at least if we use the Howland, put something here so that we can offset that DC so that these integrators work right. But this seems pretty good. Now, yeah, we have to kind of, let's compare that. So it's the same structure here. Right? But he's got the length of 1 micron and the widths here. And he's biasing it like that. When working on his, this did kind of cause some offset issues, which I think is why it wasn't working. Anyway, all these LT Spice files are here under OPAMP Design, and I think that's enough video for today.